Yes, come in.
Are you free now? Yeah, I'm fine, ma'am.
But ma'am, we need the solution for that wobbling problem. We are just breaking our head without solving it.
We even asked our friends, ma'am, but nobody is able to solve it, especially because you told we have to use the intermediate value
Yeah,
theorem.
that is the thing.
Yeah, come sit down.
Yeah.
Let's problem. Oh, yeah, we shall discuss. Oh, interestingly, intermediate value property has a remarkable solution.
We just don't get it how, ma'am. Solve.
Okay, all that you have to do is a maximum of quarter rotation.
We didn't understand, ma'am.
You don't understand?
No.
A rotation about an axis perpendicular to the tabletop. Okay, let us name the 4 feet of the table. So, let me draw this picture and then explain to you the details. So, we had a table
Okay.
having equal lengths, right?
Okay,
And it was wobbling when it was on the ground.
Yeah.
So, let us name the 4 feet of the table as A, B, C, D. Okay. Let us assume that the table has pinpointed feet
Okay.
and invariant under rotations of 90 degrees.
Okay.
Okay.
So, now that we have named the feet as A, B, C, D, in its first unstable position, let the 3 feet A, B and C be on the ground,
Okay.
and the feet D is above the ground. So, the ground level is here.
Okay.
Is the picture clear to you?
Yes.
Yes, ma'am.
So, now we make a continuous motion of rotation. So, a rotation of this table about an axis through the center of the table
Okay.
perpendicular to the tabletop through 90 degrees.
Okay.
The rotation is in such a way that A, B, C stay on the ground.
Okay.
So, this rotation brings A to A dashed and B to B dashed and C to C dashed.
Yeah. Okay.
Remember, A, B, C are on the ground.
Yeah.
The 4th foot D is above the ground in the initial position.
Yes.
After rotation, A moves to A dashed, B moves to B dashed and C moves to C dashed.
Yes.
And do you see that C dashed is on the ground?
Yes, ma'am. We can, because throughout our continuous motion, A, B, C we kept on the ground. So it will force that C dash must be on the ground.
Yes,
Yeah.
perfectly all right.
That means it is not coinciding with the point D.
D, correct. So, now to force D to C dashed,
Okay.
we perform rotation about this axis BC or
Okay.
equivalently A dashed, B dashed. This exact rotation brings A to a position D dashed. Do you understand up to this?
Yes.
Yes, ma'am.
In the initial position, right, A, B, C were on the ground
Yeah.
Okay.
and D was above the ground,
Yeah.
Okay.
and at the end of our continuous motion of rotation, D occupies the position D dashed. Is it clear up to this?
Yes.
Do you follow this continuous motion
ma'am.
of rotation?
Yes.
So, so we see that at the end of this continuous motion of rotation, the point D which was above the ground has moved to a position D dashed below the ground.
Oh.
Yeah.
Is that
Yeah.
right?
Yeah.
So, intermediate
okay.
value theorem comes into play here.
Yeah.
Yes, yes,
And
yes,
it
yes.
says that there is a position on the ground during the motion,
Or it must be on
where
the ground.
the foot D of the table will touch the ground. Since D was above the ground and D dashed is below the ground.
Yeah.
Yes, yes, ma'am.
And this enables the equilibrium of the table.
Yeah.
So, intermediate value theorem is very effectively used
Yeah.
Yes, ma'am.
in
Excellent.
saying that
Yes, really.
the wobbling table problem can be solved in the sense that you can bring the table by merely a rotation of 90 degrees to an equilibrium state.
Yeah.
Isn't it interesting?
Yes, ma'am.
Yes,
Really.
ma'am, very, very.
But you should ensure that this continuous motion of rotation is possible.
Yeah,
Yeah.
that is also a constraint.
Yes, it's a constraint.
It is always possible if the ground is flat.
Yeah, then
Yeah. In general, we have restrictions on the ground,
Yeah.
right?
who are these people? Means how they get these ideas?
No. This solution was given by Martin Gardner in Scientific American
Oh.
in
Okay.
1973, and recently there have been very rigorous proofs, and they are all available, and I'll send you the references.
Yes,
Yeah, it's a beautiful proof given by Martin Gardner. Share this solution with your friends.
Yeah.
Definitely, ma'am.
Okay, take
Sure.
them to the same canteen
Yeah.
and then try to demonstrate
Yeah. Sure.
and show that the table can be brought to an equilibrium position.
Sure,
All
ma'am.
right?
Yeah.
Then they will also enjoy this proof, right? When they see it actually.
Yeah.
Okay. Then, do I have anything else to discuss? Yes. Have you ever thought about this question? Suppose you have a real valued function defined on the closed interval, say 0, 1, and it has the intermediate value property.
Okay.
Should it necessarily be continuous?
We know that a continuous function has the intermediate value property. So
But
this
if
one.
it is having the intermediate, I think it should be continuous.
Don't be in a hurry. Think carefully. Okay, before answering this question, let me consider the following problem.
Okay.
Suppose, say, there is a function f from the closed interval 0, 1 to r such that f at 0 is greater than 0 and f at 1 is less than 0.
Okay.
Okay.
So, I have a real valued function f defined on the closed interval 0, 1 and takes values in the set of real numbers
Yes.
and such that f of 0 is positive and f of 1 is negative,
Okay.
right?
Okay.
Can you show that there exists an x in the open interval 0, 1 such that f of x is 0, given that there is a continuous function g such that f plus g is non-decreasing. Do you understand?
Yeah.
Yes, ma'am, we understood.
I want you to show that there exists an x in the open interval 0, 1 such that f of x is 0, given there is a continuous function g such that f plus g is non-decreasing. What does that mean? If x1 is less than or equal to x2, then it implies that f plus g of x1 is less than or equal to f plus g
of
of
x2.
x2.
Yeah.
So, can you try to answer this question?
I think we have to use the intermediate value property of G because G is given continuous, but I don't know what to start at all.
Okay.
That's
No idea.
completely
No
intuitive.
idea. Okay, this requires some construction,
Oh, I see.
and the solution requires some special properties of real numbers. So, let us start from there.
Okay.
So, try to recollect some good property of the real numbers.
Real numbers can be added, subtracted,
Okay.
multiplied, and they can be divided by a non-zero real number.
Anything else?
Real number has a very nice ordering property, and B is computable with that algebraic structure also.
Fine. Any other property?
If we write the real numbers in a paper on a geometric straight line, there are no gaps.
Can you say something about this in a more mathematical way?
Means, do you want to say that LUB axiom or something?
What is LUB axiom?
Oh,
Be
LUB
more
axiom.
specific.
Yeah. So LUB axiom is something like this, that if I have a non-empty bounded subset of real number, then it must be, only need bounded above. If I have non-empty bounded above subset of real number, it must have a least upper bound or supremum.
Yeah.
Fine. Exactly. So, what you are saying is every non-empty subset of real numbers which is bounded above has a least upper bound
Yeah.
or has a supremum.
Yeah.
Okay, let us look at the following example. Let us consider the set A which has elements x in the set of rationals Q
Okay.
such that x square is less than 2.
Yes.
Is this set non-empty?
Yes, obviously.
Yes. 1 belongs to this set.
Perfectly right. 1 belongs to A, so it is non-empty.
Yeah.
Any other observation?
It is bounded above, means every number must be less than 2.
Yeah. So, for every x in this set A, you have x to be less than 2. So, the set A is non-empty, subset of real numbers R, and it is bounded above by 2,
Yeah.
and therefore, it has a least upper bound.
Yeah.
Yes.
What is that real number?
It must be root 2.
Yeah.
Yes.
So, root 2 is the least upper bound of this set A.
Yes.
You are perfectly right. So, you also note that the set of rationals Q does not have
Yeah.
this property,
Yeah.
Root 2 is a
namely
rational
does
number.
not have the supremum property.
Yeah.
Is that clear?
Yes,
Yes,
ma'am.
ma'am.
So, now I have given enough clues for you to continue on this problem.
So with this clue, yeah, I think we can tell this.
Yeah. What?
The set of all x in R or in 0 1 such that f of x is greater than or equal to 0 and the set x in 0 1 such that f of x is less than or equal to 0. Both these sets are bounded above.
Yes, perfectly right.
And non-empty also, because 1 is there and 0 is in the other side.
Yeah.
Okay, and therefore,
Therefore, they must
Oh,
have the
Least
Least upper bound.
okay.
Yeah.
So, let us take alpha to be the least upper bound of the set. Say, let me call this as B. So, B is the set of all x in 0 1 such that f of x is greater than or equal to 0,
Okay.
and I call its least upper bound as alpha.
Alpha.
Yes.
Clear?
Okay.
Yes, ma'am.
So, what else comes to your mind so that we can continue with this problem? Should alpha be necessarily in B?
No,
it might not be.
Because in this previous example we saw that root 2 is the least upper bound of this set, but root 2 is not a rational number.
Yes, a good observation. So, what is it that we are given? We are given a continuous function g. So, g is continuous,
Yeah.
and f plus g is non-decreasing.
Yeah.
Yes.
This is what is given in our problem. So, what we do is, so let us now call f plus g as h.
Okay.
So, we already know that g is a continuous function and f plus g is non-decreasing, so h is non-decreasing.
Yeah.
And so, h is a function from 0, 1 to r such that h of alpha is greater than or equal to h of x, and that will be greater than or equal to g of x for every x in B. You recall this set B. What is this set B? B is the set of all x in 0, 1 such that f of x is greater than or equal to 0.
Yeah.
And we had called alpha as the least upper bound of B.
Yeah.
Yes.
So, for every x in this set B, h of alpha will be greater than or equal to h of x, because h is non-decreasing function.
Yeah.
Yes.
So, h of x will be greater than or equal to g of x for every x in B.
Yeah.
Clear?
Yes.
Further, since g is a continuous function, you can find a sequence of real numbers xn in B such that limit as n tending to infinity of xn is alpha. Okay, I repeat. Since alpha is the least upper bound of B,
Yes.
there exists a sequence of real numbers xn belonging to B such that limit as n tends to infinity of xn is alpha. Clear?
Yeah.
So, now I make use of the fact that g is a continuous function.
Okay.
Yes.
So, therefore, I have f of alpha plus g of alpha, which is h of alpha will be greater than or equal to g of xn.
Yes.
Right? So, what does this imply? This will imply that h of alpha is greater than or equal to limit as n tending to infinity of g of xn.
Yes.
So, this implies that h of alpha is greater than or equal to g of limit as n tending to infinity of xn. Why?
So,
G is
the
a continuous
Continuous
function.
function. Yeah.
So, that is it is g of alpha.
Yeah.
Yes.
So, what have we shown? If f plus g is a non-decreasing function, which we have called as h, since g is a continuous function, we are able to show that h of alpha is greater than or equal to g of alpha. So, h of alpha is f of alpha plus g of alpha. So, this immediately tells us that f of alpha must be greater than or equal to 0.
Yeah.
So,
Yes.
is it clear up to this?
Yes.
Yes. I guess that f of alpha must be 0.
Yeah. Our guess will be correct if we can show that h of alpha is equal to g of alpha.
Yes.
So, have we made use of all the information given in the problem, or have we missed out something?
No,
Till now
we
it's-
didn't use that property, no, that f of 1 is less than 0.
Yeah,
Yeah.
that property is still remaining.
Yeah.
Yeah, so now it's left to you to complete this
Okay.
problem.
So, I will add one page. So, now I have to use the property that f of 1 is less than 0.
Yes.
Yeah.
Now, what is h of 1?
No.
H of 1 is f of 1 plus
G of
1.
Yes.
Yeah.
Since f of 1 is less than 0,
Correct.
it must be less than g of 1.
Yeah.
Right.
Now,
And h is a non-decreasing function.
yes. So h is non-decreasing function. We have already proved that h of alpha is greater equal g of alpha, right?
Yeah.
So now h of 1, which is g of 1, which is greater than h of 1,
Correct.
it is greater equal h of alpha,
Yes.
it is greater equal g of alpha.
Yes. You are on the right track.
Yeah.
So you have shown that g of 1 is greater than h of 1.
Yes.
It's greater than or equal to h of alpha.
Yes.
And it is greater than or equal to g of alpha. So
Yes.
can you now say something about this h of alpha?
Yes. Now I have to use the intermediate value property of g.
No, before that say make some statement about h of alpha.
H of alpha is between g of 1 and g of alpha.
Yes.
Yeah.
Ah.
So,
and g is a
G is a
Continuous
continuous function.
yes, perfectly
Yes.
all right.
Yes, yes. So now I will use the intermediate value property,
Exactly.
and this will imply that there must exist some t which must be in the interval alpha to 1
Yes.
such that g of t must be h of alpha.
Yes,
Okay.
correct.
Now h of alpha will be again f of alpha plus g of alpha.
Okay. Now use the fact that h is a non-decreasing function.
Yes.
Yeah.
Okay.
So I'll do it.
Do you like to complete?
Yeah.
Okay.
So t belongs to the interval alpha to 1, that is t is greater than or equal to alpha.
Correct.
This gives that f of t plus g of t, which is equal to h of t,
Right.
is greater than or equal to h of alpha, and h of alpha was just proved to be g of t.
Correct.
So this says that f of t is greater than or equal to 0.
And therefore, what can you conclude?
Yeah. So t belongs to the set B.
Perfectly right.
The LUB of the set B is alpha.
Correct.
So from this we see that t is less than or equal to alpha.
Correct.
But t was already greater than or equal to alpha.
Yes.
This says that t is equal to alpha.
Yes.
Yeah.
So, and therefore, what do we conclude?
So we have that. So from this statement we can see that g of alpha is equal to h of alpha, which is equal to f of alpha plus g of alpha. So this says that f of alpha is equal to 0.
Yeah, your guess was correct.
Yeah.
Earlier we proved that f of alpha greater than or equal to 0.
Yeah.
But the fact that f of 1 is less than 0 and the property of h that it is a non-decreasing function leads to f of alpha equal to 0.
Yeah.
Clear?
Yeah.
So, what is it that we have shown? We have shown that if we have a real valued function f defined on the closed interval 0, 1, that f of 0 negative and f of 1 is positive, then it has the intermediate property that there exists an x in the open interval 0, 1 such that f of x is equal to 0, given that there is a continuous function g such that f plus g is a non-decreasing function.
Yeah. But actually it does not answer our original problem, no?
Yeah.
We are using the help of another function g to do this.
Yes, sir. This example shows that the intermediate value property may not imply continuity. Is that okay? So, we have discussed in detail this example of a function f of x which is sin 1 by x
Yeah.
for x not equal to 0 and it is equal to 0 when x is equal to 0. Have we not discussed this?
Yes, this function is continuous everywhere except at the point 0.
If you plot the graph of this function f of x,
Yeah.
what does it show?
Oh, yeah, it must satisfy the
graph of the
intermediate
function
property.
shows that it satisfies the intermediate value property.
Yes.
So, here is an example of a function which has the intermediate value
Yes.
property but is not continuous.
Yeah.
Yes.
In fact, one can show that the function f of x given by sin 1 by x, x not equal to 0, it is equal to say some a for x is equal to 0 has the intermediate value property if and only if A is such that it lies between -1 and 1.
Okay.
Yeah. So you should be able to solve this problem and give me
Yes,
the
ma'am.
solution when you meet me again.
Yes,
Yeah,
ma'am, sure,
okay,
we'll
ma'am.
try.
Isn't it? So the
But I
question.
think it should be very
So I
easy.
expected that you would answer me when I gave you the question. Suppose a real valued function defined on the closed interval 0, 1 has the intermediate value property. Should it necessarily be continuous?
Yeah, we
I
should have.
expected that you would jump
we,
up
we
with
should have, we should
this.
have. We discussed this in more detail.
yeah.
Still, we couldn't give this example.
Anyway, we were able to get an example of a function which it told us that the intermediate value property may not imply continuity of the function. Yeah, yeah, good. I think we have almost covered all the nice properties of continuous function defined on an interval, which is a subset of a real line. So we will think about some more topics and some more concepts in our future meetings. We
Okay.
will close with this for today.
Okay, ma'am.
But these discussions are really helpful.
Yeah, you please go and share all these information and discussion with your friends.
Sure, ma'am.
See you.
Yeah,